Finding the extrema of a function, because it is not always practical to plot functions and look for extrema. We use calculus to find local extrema. The key insight is that for functions that are continuously differentiable, the slope of the function at any interior minimum or maximum is 0. Figure capital A dot 7 illustrates that the slope of the graph at every interior local minimum or maximum is 0. Because derivatives can be thought of as the slope of a function, one way to find all the interior local extrema of a continuously differentiable function is to find where the partial derivatives of the function equal 0. Let us begin with a problem that has only a single independent variable and f colon open bracket 0 comma 1 close bracket yields all real numbers, where f is assumed to be continuously differentiable and strictly concave. What is the importance of these assumptions? In figure capital A dot 6, we have interior extrema. There are two panels. Panel A is interior maximum. There's a horizontal x-axis, and there is a concave line, moderately concave, that intersects the x-axis at 0.5. And the text reads, in panel A, the maximum point A occurs at x equals 0.5, which lies in the interior of the interval, open bracket 0 comma 1 close bracket. In panel B, the maximum at A is at the corner, not in the interior of the domain. And B, panel B in figure capital A dot 6, interior extrema, has a concave curve sloping downward, but the maximum is at the corner, at the origin. In figure capital A dot 7, extrema, and the first order condition, capital F, capital O, capital C. If a function is continuously differentiable and concave, it must have a unique maximum. Further, if the capital F, capital O, capital C has a solution, that is, the function has a point where its slope is 0, the first order condition characterizes the unique maximum. A, this function is continuously differentiable and concave, so the first order condition identifies a unique maximum at point A. In panel B, the function is continuously differentiable, so it has at least one maximum. But the function is not concave, so the maximum may not be unique. Indeed, there are two maxima at the endpoints. The function is convex, so the first order condition characterizes a minimum. In panel C, the function is continuously differentiable, so it possesses a maximum in the interval open bracket 0 comma 1 close bracket. However, at point A where the first order condition holds, the function is neither concave nor convex. So A is neither a minimum nor a maximum. It is a saddle point. Panel D, the function is concave, so the maximum will be unique. However, the first order condition does not have a solution in the interval 0 into interval open bracket 0 comma 1 close bracket. There is no place where the function has a slope equal to 0. So the unique maximum is not characterized by the first order condition. End of figure capital A down to 7. There are two important consequences of our assumption that f is continuously differentiable. First, because f is continuously differentiable, it must also be continuous. So we know that it has a maximum. Second, because it is continuously differentiable, we know that its derivative exists. And hence we can use this derivative to determine the local extrema. Because f is assumed to be strictly concave, we know that it has a unique global maximum. Thus, if we find a point x where the derivative of f of x with respect to x equals 0, it follows that this point x is the unique global maximum of the function f over the interval open bracket 0 comma 1 close bracket. The usual way to write the problem of finding a maximum of a function f of x is max with an italics x underneath the max f of x, where max is called the max operator. The variable x that appears below the max operator is the choice variable, and f is the function to be maximized and is called the objective function. Any x star in open bracket 0 comma 1 close bracket that solves the derivative of f of x star with respect to x equals 0 is a point at which the function f of x has a local maximum. The equation derivative of f of x with respect to x equals 0, in which we set the first order derivative equal to 0, is called the first order condition. The x star that solves this equation, the derivative of f of x star with respect to x, is called a critical value. Given our assumptions that f is continuously differentiable and concave, we know that x star is a unique global maximum. So far, we've assumed that f is concave, as in panel A of figure capital A dot 7. In practice, we need to check whether the function is concave. For example, if we falsely assume that the function is concave and it is convex, we may find a minimum rather than a maximum, as in panel B. If f of x star is at least twice differentiable in a neighborhood of x star, we can use the second order condition to determine whether the function is concave in that neighborhood. The second order condition for concavity is that the second derivative of f of x star is negative, where you have the second derivative of f of x star with respect to x is less than 0. If this condition holds, we know that the x star that the first order condition identified is a unique maximum in this neighborhood of x star. In contrast, if the second derivative is positive, we know that the function is convex in this neighborhood and that we have found a minimum.